So on 4.3b, we saw how the second derivative can help us determine the concavity and the points of inflection for a function. Today, when we wrap up 4.3c, we'll see how the second derivative test itself is also valuable for extrema. So not just concavity, not just points of inflection, but also determining whether something is a maximum or a minimum. So we want to go back to think about what every maximum has in common in terms of its concavity. So if we look at all the maxes here, we see that all of the maximums are sitting on top of sections that are concave down. And so we would say a max is part of a concave down interval. Similarly, a minimum is part of a concave up interval. It's sitting there at the bottom of a piece of the function that has concavity that is positive. So a min is part of a concave up interval. So that leads us to the second derivative test. The presence of a max can be detected at a critical point if the second derivative is negative. And then similarly, the presence of a min can be detected at a critical point if the second derivative is positive. And so if you find the critical points, A, B, and C, okay, so remember, a critical point is found by setting the first derivative equal to 0 or f double prime equal to 1 over 0. So if you've already done that, then you plug those not in interval, but you plug them directly in. And if you get a plus or a minus or a plus, okay, that means that A is a critical point and is sitting on top of, sitting in an interval with positive concavity. So if A is a critical point and sitting in an interval of positive concavity, then A is a min. If X is B is a critical point and sitting on top of a negative concavity interval, then we have a max. And then if X equals C is a critical point and sitting within a positive concavity interval, we have a min again. So this is a quicker way to check a max or min. Rather than looking for a change in an interval, you're just looking at the value itself. So now we've got three tests. We have the candidates test, we have the first derivative test, and we have the second derivative test. These tests are all for extrema. The candidates test doesn't use a derivative. It takes the critical points, but it checks the y value of the end, and it's best when you have an endpoint interval. Okay, so it checks the y value of the endpoints and the critical points, and you just compare y values. The first derivative test, you find the critical points. You're checking the interval values for a change. In the second derivative test, you take your endpoints and your critical points, and you're not checking an interval, you're just checking the second derivative value to determine the concavity and find extreme values. So to summarize, if f prime of c is equal to 0, and I would also add to that, or f prime of c is equal to 1 over 0, and if the second derivative is a negative value, then we have a maximum, and you should picture that. Okay, horizontal tangent, negative concavity. If f prime of c equals 0, or I would add f prime of c is undefined, and the concavity is positive. Okay, so has both horizontal tangent and positive concavity. Then it's the presence of a minimum. So while you're practicing, you might just want to sketch. Okay, I know it has horizontal, and I know it has this kind of concavity. So let's practice using the second derivative test. We need both the first and the second derivative, but we're only going to test the second derivative. So I need the first derivative. (3x squared minus 6). I need the second derivative, 6x. From the first derivative, I will get the critical points. Okay, the critical points are plus or minus rad 2. So I'm going to check. So I know that f prime of rad 2 is 0. And now I want to check what f double prime of rad 2 is. That's 6 rad 2. That's a positive number. So if you've got the first derivative equal to 0 and the second derivative positive, that means you have a horizontal tangent with positive concavity. So x's rad 2 is identified as a local min. Let's check negative. So we've got f prime at negative 2, that is equal to 0. And f double prime of negative 2 is equal to negative 6 rad 2, which is less than 0. So now we have both a horizontal tangent and negative concavity at x's negative rad 2. And so that is now a local max. All right, so that is how you use the second derivative test. All right, we're going to finish up with practicing some graph reading. Some of you answered incorrectly on the last chapter test because you read the graph literally instead of figuratively, okay? Literally, if I said literally, what are the maxes and the mins? You're like, oh, min, min, max. Okay, that would be a literal reading of this graph. Okay, but I'm not asking you to read this literally. We're reading it figuratively because you will be told this is the graph of f prime. So then you've got a max here, a min here, and neither. Oops. All right, so it's important to understand the definition of what you look for. Don't trust your eyes, trust the definition. A max is when f prime of x equals 0 or f prime of x is 1 over 0 and changing from positive to negative. That's how I knew that that was a max. Because f prime, which is what I'm looking at, was equal to 0 and changing from positive numbers to negative numbers. A min is when f prime is equal to 0 or f prime of x is equal to 1 over 0 and changing from negative to positive. That is how I identified that as a min so quickly. And the way I could classify the origin as neither is because although f prime of x is equal to 0, there is no change. It's a negative staying negative. So go back and write the definition out and then look at the graph. All right, so we have determined, find the x coordinates where we have a maximum. So we determined that the x coordinate where we have a maximum is x is negative 2. The minimum we determined is x is positive 2. Therefore, between that max and min, we should be able to find the intervals of the x values on which the function is increasing and decreasing. So it will be rising or increasing every time it's above the x-axis. Every time the derivative is positive. The definition of increasing when f prime is positive. So what you're looking at is above the x-axis. Decreasing, the definition is when f prime is negative, so what you're looking at would be below the x-axis. So we can say that this function is increasing every time x is less than negative 2 and every time x is greater than positive 2, and it is decreasing between negative 2 and positive 2. Find the x coordinates where f prime has an inflection point. All right, now we haven't done this before, this is new. But let's go back to what an inflection point is. An inflection point is where f double prime changes from positive to negative or negative to positive, either way. So now I want to swap out f double prime for its synonym. F double prime is the slope of f prime. So I can say, okay, an inflection point is happening where the slope of f prime changes from positive to negative or negative to positive. Where does the slope of what I'm looking at change? So I would say right there is the first time that the slope changes from negative slope to positive slope. Again, it changes at the origin from negative slope to positive slope to negative slope, and then again changing here. So my inflection points are happening at x is, okay, that's roughly, I'd say negative 1.4 and 0, and then positive 1.4. Okay, now let's do concave up. Concave up is where f double prime is positive. So then change f double prime to where the slope of f prime is positive. Well, I see two sections of positive slope. This section has positive slope, and this section has positive slope. So it is going to be concave up on the interval between negative 1.4 and 0, and also on the interval from positive 1.4 to infinity. And then the definition of concave down, where f double prime is negative. Okay, that's the definition. Swap out the definition of f double prime for the words slope of f prime. And if I'm looking at f prime, the slope of this f prime is negative on these two values. And so that means the original function will be concave down on those two places. And so concave down would be anytime x is less than negative 1.4 or between 0 and positive 1.4. Okay, let's try that again. Try a new graph. Okay, this is hard. Okay, yes, this is hard. It just takes practice. So we are looking, here's a graph that is identified as a derivative graph. So when I say find the maximum, I don't mean this point. That is not the maximum. A maximum, by definition, is where the derivative is either 0 or undefined. So I see, here's where it's 0 at A, here's where it's 0 at B, here's where it's 0 at E. It is undefined because of the broken asymptote at F, and it is 0 at G. So I have 5 places of x coordinates that are important here. Not only does a maximum need to have a derivative that's either 0 or undefined, but the derivative must also be changing from positive to negative. So I see this derivative changing from positive to negative. The only other time I see it changing from positive to negative is at G. So the local maximum values are at C and G. A minimum value is when the derivative is changing from negative values below the x-axis to positive values above the x-axis. That happens here from below to above. It happens at E from below to above. And at F, it stays above the x-axis on both sides. So the only minimum values are going to be A and E. And now I want to identify values of which the original function is increasing. The definition of increasing means that the first derivative is positive. If the first derivative is positive, the graph I'm looking at must be above the x-axis. So it is entirely above the x-axis from A to C. It is again above the x-axis from E to F. And then finally, it's above the x-axis from F to G. The original graph will be falling whenever the derivative is negative, which means where the graph of the derivative that I'm looking at is below the x-axis. So it is below the x-axis when x is less than A, between C and E, and then when x is greater than g. Now we want to look at this derivative graph and answer questions about inflection points. Okay, let's go back to the definition of an inflection point. An inflection point is when f double prime changes. So remember, we're going to change f double prime to the slope of f prime. So let me rewrite this. When the slope of f prime changes. So let me highlight the different kinds of slope. We have positive slope, followed by negative slope, followed by positive slope, and then negative slope. So anytime I changed colors, and so my inflection points are going to be happening at B and D and at the asymptote of F. And now it's pretty easy for us to tell, because I've color coded it, the values where where the function would be concave up. So any section that had positive slope would be concave up. So concave up would be x less than a, and from D to F. And concave down would be B to D, and then anything greater than F. So feel free to screenshot graphs, to color code them, to draw on them, but always go back to the definition and don't just trust your eyes. Okay, always go back and how is that defined? How do I define inflection point? How do I define concavity? How do I define maxes or mins? And that usually will help you as you get more experienced reading a first derivative graph. All right, I'll see you guys on Friday.